Hi everyone, welcome back. I hope you watched the previous tutorial on the topic of performing this color normalization using a template image, where we have a template image and we have a whole bunch of input images that we want to look like this template image. So we perform certain operations, which is very simple. You take the mean and standard deviation of your template image, same for your input images, and you do normalize your input images to the same mean and standard deviation through all the three channels. And we converted our input images to lab space because in RGB space, R and G and B are not independent, but once you move it to lab space, they're a bit more independent than RGB. Okay, why am I explaining all of that? I should probably request you to go back and watch that video. And also, if you are already a subscriber, you probably did watch that. If you're not a subscriber, this is a great time to hit the subscribe button. And if you are extra generous, just find that thanks button right next to the subscribe. With that background information, let's discuss what's going to happen in this tutorial. I am going to talk about how you can effectively augment your histology images. Probably applies to all any other type of images, but primarily for histology images where you have your input images often with some diverse look and feel. Like you can see how this image looks a bit washed out and this one looks different, this one looks different, and the differences come for many reasons. We don't have to worry about that or talk about it in this tutorial, but whatever the differences are, how do we handle those? One, you can follow the method that I talked about in the previous video. You can convert all your input images into a similar look and feel space. So that is, you're pre-processing your data. And then you're training your deep learning model to do your classification or segmentation, whatever task you would like to do. And why do you need to pre-process? Because when you train a model, you want the model to be as generalized as possible so it works on all your future images. And all our attempt is that we're trying to do here is either pre-process your data to bring your images to the same look and feel, or you augment your data to represent all of this. And this is exactly what the focus of this tutorial is. We are trying to look at how we can actually augment that, or what are the strategies that we have to augment these different looking images. So we're taking them from this look and feel to a different look and feel, but then this is what goes into training your deep learning model. Now, when you do that, you're training your input images. Obviously, you're doing all these random transformations, right? So in this round, in this batch, this image may look like this. In the next batch, the same image may have this look and feel. The same image may have a different look and feel. It's basically, let's say you have 5 different styles that you're trying to optimize your deep learning model or generalize your deep learning model. We're trying to generate all those 5 different style images using the input data that we have. So this is another strategy. I'm not a genius enough person to come up with that strategy. In fact, it came this is the original paper. Find the link as part of the description to go through, read this in detail, but I really liked it, so that's exactly the reason why I'm making this video. So all credit goes to these guys, and they have a GitHub link. I took some code from here, not all of it. I modified my code to make sure it's easy for you to implement without doing much effort. Yeah, I'm going to walk you through the code that I have obviously in this video, but what are they proposing right there? So let's go through this, because this gives us a good idea of what exactly are we trying to do. So this is stain variations often decrease the generalization, obviously, right? So for the ability of deep learning in digital histopathology, blah, blah, blah. So to address the problems, they unify the stain normalization and stain augmentation, these two processes. It's not just normalization. So think of the previous video and add stain augmentation to this one. But then within a given space, right? Did they mention that here? With a novel scheme, which constrains the variable stain styles in a practicable range, right? So because otherwise, if your images are, I don't know, stain augmented in blue and yellow and all these different spaces, that will never happen in your real life samples, then that's not a good way of generalizing your model. So basically, you need to know the space within which you need to work with. That's exactly what these guys are proposing. And of course, let's go through a couple more slides. So you have your input images that look very different, like the ones I showed you in the last video. I'll also show you some images before we jump into the code. And the conventional approach is, okay, you do your stain normalization, so all images look the same. my previous video, exactly like that. I don't see not anything wrong with that. As long as you're bringing all your images that look into the same look and feel, and you do your future images pretty much the same thing, right? So they're combining that with stain augmentation, because if you just do stain augmentation, whether you're using torch vision for your augmentation or TensorFlow, your images can be augmented in color, like in yellow, blue, all these different spaces, but in reality that's not reflecting your real life scenario. So they're combining these two to make sure that you define a space within which you can actually do this augmentation and the normalization, and your output images, just like I showed you in the previous screen, they have all these variations in look and feel, but those are real variations that your future images may look like, depending on sample prep, or depending on tissue thickness, and many other factors, as you probably know. Okay, so that is the high level goal, and here is again another screen that actually shows you the overall pipeline. So what you can do is you can create a data generator, so you get like these random images generated that are sampled from this specific space that you're defining up here, and those images can be augmented, as you can see, and the augmented images are fed into your classification or segmentation or whatever you want to do with your image processing. And the key aspects here is stain style creation and characterization. What did they do? They actually converted the images to your lab space, and once it's in the lab space, they take your average or mean and standard deviation. This is basically what I described in the last video, and we called it Reinhardt approach, and that's exactly what they're doing right here. Yeah, so you have a reference image, except in the previous video, we looked at a reference image and we said all my input images look like reference image. But in this case, these guys are basically saying, okay, dump all your reference images into different folders, where each folder, like for example, has a specific look and feel. If I go back, oh, I don't need to go back here. So you have like one set of images that look like this, another set of images that look like that, and another set right here, another set right here. Then during the augmentation process, it is going to randomly sample one of these, get the statistics, and then your output image or the augmented image is going to look like that. In the next round, it's going to randomly do one other, and so on. Basically a typical augmentation scheme there, right? And virtual stain normalization template. Again, this has been discussed. Again, once we get to the code, I'll talk a bit more about it, but I just included a few screenshots over there. Okay, let's jump to the code and look at our images and continue with the video. And before continuing with the video, I just want to quickly flash the screen, on the screen, the original paper right there. You can go ahead. This is just from June 2022, an year ago, right? I mean, less than a year ago right there. And you can see that you can read the entire paper. Like I said, it comes down to a couple of steps, which I'm going to show you in a minute. And they also have the code. I did not clone the entire repository. I only took the main.py and RandStainNA, these two. That's pretty much it. And I also took the code from this pre-process. I edited this. I edited all of that. So I'll share my modified versions of this code so you can look at exactly what's going on. I'm going to explain these 3 steps. And I think they also included like this classification and segmentation to show you the examples of how you can use this as part of an augmentation scheme while you're doing classification and segmentation. But I'm pretty sure most of you know that. I'm just focusing on the technique itself and not just including that as part of augmentation. Okay, now let me open my code. Let me open the images. So what I have here, first thing first, I have a directory called data, and I have all my original images here. Okay, and the goal is to do augmentation, but first let's actually look at how the images would look like if I only do stain normalization, if I only do stain augmentation, but then again follow these guys' code to see how the augmentation looks like. It's pretty quick. Stain normalization, I have done this in the last video. This is exactly the same code. I haven't modified or anything. Let me actually, I should have modified this. I should have modified this before this video. I just copied that in here. So let me pause the video, edit this code a little bit to make sure that it is looking at the right directories right there. Yeah, it isn't right now. So excuse me for a minute. I'm going to pause the video anyway, so it's not going to waste your time. Sorry about that. Okay, I'm back. All I did was just point my input directory and the template image and output directories to the right location. So let me make sure I'm working in the right directory. Stain master, yeah, that's exactly where I am, and within that I want to look at data. Sorry about that, should have been a bit more prepared. So let's go ahead and run this. All this is doing is only stain normalization using the Reinhardt color transfer method, and again I explained that in the last tutorial. All we're doing is looking at the template mean, template standard deviation, input mean, input standard deviation, and then just normalizing it. So when I do this, I mean, obviously we are done right there, and I forgot to mention that I'm using 3.png as my input template. So what does that mean? So if I go back to my original, this is the look I picked as the template, and these are all the input images. And stain normalization, so there you go, all images look pretty much the same, right? So this is just if you want to, I mean, this is a repetition of what I did in the last video. Now let's go ahead and do the augmentation only, the color augmentation. You can do that in, what did I do it in? PyTorch. The PyTorch code again is, I believe, from the same repository as these guys. Stain augmentation, just a few lines of code. Again, as usual, I modified it to make sure it's easy for you to execute locally. But if you want to use TensorFlow, if you're a TensorFlow person, you know how to do that, how to augment your images, right? So that's what we're doing. So here we are using Torch Vision to import our transforms, and within the transforms, you know, color jitter right there, and within that color jitter, the parameters that we are going to change are the brightness randomly by 0.35, contrast 50%, saturation 50%, hue by 50%, and then we are going to save the output in a different directory. And let's go ahead and run this. It should be pretty fast. We only have like 7 images right there. And let's go and open stain augmentation, and as you can see, not share, view, large, they look all nice and disco-y. So for natural images, this may look okay, but yeah, I don't think you'll ever see a pathology images that looks like any of these images. In fact, maybe this one is okay. This one is probably okay, but you'll never see pathology images like this. So what's the point in augmenting your data like this and training your model and compromising potentially on your accuracy? So there is no point. So how can we constrain that space and still do color augmentation with respect and normalization together? That's exactly what this stain-NA is all about. Now, one thing is this code actually uses a YAML file where we described certain aspects, certain parameters. And this YAML file, do I have it? Let me go back to preprocessed statistics, output, yeah. Let me open that so I can show you what's inside here. So it shows you the distribution of L channel, A channel, and B channel. Remember, we are converting our images from RGB to LAB space, and it's going to show you the average and standard for, you know, the mean and standard deviation, and all the required statistical parameters for us to generate new images. Now, how do you get this YAML file? So first, let's focus on that. Yeah. So the way again, I'm just following what these guys did on in their paper and the code that they shared. So the code that I'm going to show you right now is the part of this pre-process. So what does that pre-process do? So within the pre-process, let me go back. Let's delete the output. So we create a new YAML. Okay. So I opened this file, this Python file right now, and I have a folder called train, and within train I have multiple directories, and well, in this case 2. I dumped some images that look like style 1 in style 1 and style 2 in style 2. You see how these are more pinkish? So these are different styles, and you may have like 6-7 different type of images, and you can give appropriate names right there, but I just gave them a style 1 and style 2. Now in this code right here, the statistics, I need to point it at the path to my train or path to my these template images, And that's pretty much it, and where to store your YAML file right there. And I usually, for not change anything else, randomize equals to true means, hey, go ahead and pick the random image from that directory and then as the template. So that's what it's doing right there. Everything else is basically extracting the statistics like mean, standard deviation, and all of that. And towards the end of it, it actually creates the YAML file. No point in going line by line. This is not how to do Python stuff. This is not Python basic stuff, but basically a technique, a process that I'm trying to explain here. Okay, so with this information, let's go ahead and run it. And it should save a YAML file. You see how it's actually fitting these two distributions and captured all the information into this YAML. So if I go to output, so that is the file that we are going to use. And again, let me go ahead and open. You can see how that's organized right there. Okay, so that is one of the inputs that goes into our main program. Now, let me close this to make sure we are focused. Let's clean everything up. Let's clear the screen. So now we have a YAML file. Yeah. So again, we're not using one reference here. You can, but we are basically saying, hey, take a random image. This is a great way of augmenting, right? So when you're doing data augmentation, you want to randomize this look and feel. Now it knows what the look and feel should be. It has the YAML file. So it takes that as an input right there. And now as part of my main file, I'm actually saying, okay, my directory path is right there, and my save the output into the augmented directory. And what is it doing for each of my images? It's actually just taking my brand StainNA and reading the images, doing its transformation, and then go ahead and saving it. And if you look at their image, if you look at their main program right there, again, you can go ahead and download this. I'm going to obviously put a link to the original source. I am just doing this part, the top part, which is, hey, just randomly generate an augmented image and show me, or save it to the local directory. But if you want to use it as part of your training process, here is how you can create your transforms object, and you can include that as part of your transformations, and you can do exactly the same even for TensorFlow. Okay, so let's see how this augmentation will look like, and we are calling this this method from this file right here. And again, you can see how it's actually looking at the YAML file to get all the statistical parameters, and then here is the main function that's actually doing the job. And it's simple. I mean, it may look, again, go through the code, but it's basically looking at the standard, mean, and it's actually it's doing this. I keep forgetting the Reinhardt, yeah, sorry. And it performs this Reinhardt color transform. And in addition to that, it also adds this other color transform that we talked about, augmentation step right here. And it gives you a batch of images whenever you call that augmentation step. Okay, so let's go ahead and run this to go save our augmented images. It's pretty fast, as you can see. Now let's open, let's go back. So you know our original images. Let's open it. These are our original images, and the augmented images. Open a new window. So there you go. This is our augmented images. And now these augmented images, they look reasonable. These really help us in generalizing our input data model. Maybe the first two have a bit of a yellow shade, but look at all the other ones. And this yellow shade is probably coming from our train images, and you can even more narrow down, this space by putting appropriate train images. So let's go back to look at the stain augmentation. If you just do the stain augmentation, this is how the images are going to look like. If you just do the stain normalization, this is how the images are going to look like. They look pretty standard, nothing wrong with that. But when you combine them both, this is how the images are going to look like. And they're going to help you generalize your model better. Okay, I think that is it. That's what I planned, and I really hope you enjoyed these two videos, like the last one and this one. And let me know if you like these type of videos, that are more on the application side rather than talking about, how to build a unit or how to do this and that. And another thing that I often get asked is, hey, can you do like image segmentation using something new published paper from, a month ago or something? I'm not an expert on all the new papers. I mean, I try to read them, but my philosophy is focus on the task that you're trying to do. Is your task identifying, segmenting trees and buildings, segmenting nuclei? If so, unit does an amazing job. Then what type of data do you have? Focus on collecting the right data. Focus on the right pre-processing steps and right augmentation steps. I think better data definitely beats better models, whatever the better is. So unless there is anything disruptive when it comes to image segmentation or object segmentation, I'm going to rely on mask RCNN and Stardist and CellPose and some of these standard techniques. And that reminds me, I should do a video on CellPose because it works great on segmentation of cells, but it also works great on a few other segmentations. So expect those videos in future. Thank you guys, and see you in the next video.